Good day to you children. In today's class, we'll be learning about mass and weight in the beginning. So, what are mass and weight? So far, we have learned that we have used the terms mass and weight interchangeably. We kind of use them as the terms with same meaning, but both are different. Mass. First thing, mass is the total amount. It is the total amount of, or it is the total matter, it is the total matter or total amount of matter contained in an object. Say for example, you go to the market and buy 1 kilogram of tomatoes. So the mass of the tomatoes is 1 kilogram because it contains 1 kilograms of matter in that. So weight means weight is the force. Weight is the force with which an object is attracted towards the earth. So, mass is the total amount of matter contained in an object and weight is the force with which an object is attracted or pulled towards the earth. That is weight. And weight is given by W is equal to mass into acceleration due to gravity. Weight is equal to M into G. This is the formula for calculation of weight. So these two definitions, based on these two definitions, we can differentiate mass and weight as mass remains constant throughout the universe. If you weigh 65 kilograms on earth, then on moon your weight will change. On Mars your weight will change because the gravitational attraction or the gravitational force of those planets or heavenly objects is different than that of earth. Similarly, Jupiter is massive compared to earth. So because of that, what happens? Weight on Jupiter is hundreds of times greater than weight of an object on earth. So weight is constantly changing based upon the pull of gravity of the planet, whereas mass remains constant no matter where you go. Mass of an object or the amount of matter present in an object remains constant. So that is why weight is given as product of mass and acceleration due to gravity G. We know the value of G is 9.8 meter per second square on earth. But since whenever we measure our weight on earth, if you measure our weight by going to America or Russia or Japan or here itself in India, our weight is same no matter where we measure it on the earth. That is why, since we will be staying on the earth forever, we will use mass and weight interchangeably. We will say that the weight which we measure on the earth is equivalent to our mass. And since weight is a force, its SI unit is as we know, SI unit of force. SI unit is Newton. Denoted by capital N. So now let us compare weight of an object on earth and that to its weight on moon. So we know that yesterday we learned that mass of earth is mass of earth is equal to 5.98 into 10 raised to 24 kilograms. And also mass of moon is equal to 7.36 into 10 raised to 22. Almost 100 times difference. 100 times lighter compared to earth. Moon is 100 times lighter because it is 10 raised to 24, whereas this is 10 raised to 22 kilograms. These are the masses. So obviously, which is heavier of the two? Earth is heavier. Mass of earth is greater. So because of that, since the mass is greater, the gravitational pull of earth is also greater, because from the law we learned that the force of gravity is always proportional to the product of masses. So that is why, since mass of earth is greater, its gravitational pull will be greater. Similarly, we know that radius of the earth, RE, is equal to 6.37 into 10 power 6, and radius of the moon in meters, this is in meters, and radius of the moon is equal to 1.74 into 10 raised to 6 meters. So these are the radii of earth and moon respectively. So now weight on moon will be, weight on earth is mass of an object into its gravity, acceleration due to gravity. So now weight on moon is nothing but it is the gravitational pull, right? It is a force, right? So weight on moon is equal to gravitational constant G, using the universal law of gravitation. Weight on moon, it is nothing but a force. So force is equal to gravitational constant into mass on earth, mass on moon, mass of moon into mass of the object divided by radius of moon. This is the equation for weight of moon using the universal law of gravitation. Mass of moon into mass of the object divided by radius of the moon squared. Radius of the moon squared. So this is the weight on moon, or the gravitational pull that an object experiences due to its presence on moon. Similarly, weight on earth will be equal to universal gravitational constant G into mass of earth into mass of the object divided by radius of earth squared from the universal law of gravitation. So now comparing both of them, weight on moon to weight of earth, taking the ratio, we get G into mass on moon into m by rm squared whole divided by weight on earth. Weight on earth is this much. G into mass on earth into m, mass of earth into m by radius of earth squared. So G constant cancels out, m cancels out constant. It's the same object. We are measuring the weight on earth and weight on moon for the same object. So m is same. It cancels out. What we will get is weight on moon to weight on earth is equal to mass on moon, mass of moon by radius of moon squared into rm squared into re squared by mass of earth. This is what we'll get. Now we know all the values. We just wrote all the values: mass of earth, mass of moon, radius of earth, radius of moon. Now we will substitute them to see how much the difference between both the masses, both the weights will be. So substituting the values, we get mass of moon is 7.36 into 10 power 22 divided by radius of moon is 1.74 into 10 raised to 6 into radius of earth, this is squared. Radius of earth is 6.37 into 10 power 6 squared divided by mass of earth is 5.98 into 10 power 24. So now simplifying the whole thing, we get weight of moon to weight of earth is equal to 1 by 6. We'll get this value. It means the force of gravity on moon is 1 by 6th that of compared to the force of gravity on earth, or in simpler words, if an object weighs 6 Newton on earth, if an object weighs 6 Newton on earth, then it will weigh 1 Newton on moon. So this implies greater the mass of the planet or the star or some celestial body, greater its mass, celestial body, stronger is the gravity. Stronger is its gravity. Thus weight will be higher. Weight will be higher. Now we have some examples here. Example 10.4. Example 10.4, in which they are given that mass of an object is 10 kg. So mass of an object is 10 kg. What is its weight? What is its weight on earth? So to calculate weight, we know that weight is equal to mass into acceleration due to gravity, g, and we know the value of g to be equal to 9.8 meter per second square. Don't forget the units. So since we know the value of m and g, directly substituting, we get 10 into 9.8, which is equal to 98 Newton. So if mass of an object is 10 kilograms, then its weight on earth is 98 newtons. This is the solution. The weight on earth is 98 Newton. Now moving on to solved example 10.5. 10.5. An object weighs 10 Newton when measured on the surface of earth. So weight on earth for an object is equal to 10 Newton. So what would be its weight when measured on the surface of moon? So weight on moon is equal to how much? Just now we saw that if an object weighs 6 Newton on earth, then it will weigh 1 Newton on moon. That is, the ratio between the weights is 1:6. So now to find its weight on moon, all we have is weight on moon. We know that weight on moon is to weight on earth is equal to 1/6. We know weight on earth, so weight on moon by 10 is equal to 1/6. So now this implies weight on moon is equal to 10/6, which is equal to 1.67 newtons. So this is the solution. So weight on moon, weight of the object on moon is 1.67 Newton. This is the solution. So now look at example 10.2. Solved example 10.2. We have a car falls off a ledge and drops to the ground in 0.5 seconds. So t is equal to 0.5 seconds. We are going to make use of the equations of motion which we learned in the previous class to solve these questions. Right. So, and let g is equal to g is equal to 10 meter per second square. The value of g is interchangeable. If they have given g is equal to 10 meter per second square, then use that value. If they have not mentioned the value, then you should put g is equal to 9.8 meter per second square. So now here we have to find out first what is the speed on striking the ground, that is final velocity v. First we have to calculate v, then we have to calculate its average speed, and lastly we have to calculate how high is the ledge from the ground, that is the height from which the distance from which the car hit the ground. So to do that, first we know that since the car is falling at the top of the ledge, its speed is 0 per meter second. So initial velocity is 0 meter per second. So to find v, we know that v is equal to u plus at, u plus gt. Since the car is falling, it is performing a free fall. So instead of a, we will be using g, which is constant and whose value we know. So this is equal to u is 0, 0 plus 10 into 0.5. So which is nothing but 5 meter per second. Therefore, the final velocity of the car on hitting the ground is 5 meter per second. Similarly, second, we need to calculate the average speed, v average, which is equal to u plus v by 2. U plus v by 2. So now we know that u is 0, v is 5, 0 plus 5 by 2, which is equal to 2.5 meter per second. And lastly, we need to measure the distance traveled by the car, or the height of the ledge, or height from which the car fell. So to measure distance, we have two formulas. One is v square minus u square is equal to 2gs. Otherwise, we can also use s is equal to ut plus half gt square. I am using g here. Once again, I am repeating because the car is performing a free fall. So s is equal to, let us make use of s is equal to ut plus half gt square. So here, since we know u is equal to 0, since we know that u is equal to 0, then this first term will be 0. So the whole thing will reduce to half gt square. So s is equal to half into 10 into 0.5 square. 2 ones are 2 5s are 0.5 into 0.5. On simplification, everything we get s is equal to 1.25 meters. So these are the required solutions. First, the final velocity on hitting the edge is 5 meter per second. On hitting the ground is 5 meter per second. Then the average speed is 2.5 meter per second. And lastly, the height from which the car fell, or the height of the ledge from the ground, is 1.25 meters. And now coming to solved example 10.3. In the solved example 10.3, we have an object is thrown vertically upwards and rises to a height of 10 meters. So since they are talking about height, it is nothing but displacement. So s is equal to distance or displacement. You can both use them interchangeably here. So s is equal to 10 meters. Calculate. First, we need to find velocity with which the object was thrown upwards. So here we need to calculate u, initial velocity. Remember, when something is thrown upwards, after reaching its maximum distance or maximum height, the velocity of the object will become 0. That means its final velocity will be v is equal to 0 meter per second. Before falling down, the velocity reduces to 0 and then it gradually increases. So now, and second, we need to find the time taken by the object. T is equal to how much? So since the value of g is not given, so take g is equal to 9.8 meter per second. And acceleration of the object in upward motion is, since acceleration due to gravity Coming downward is positive. Moving upward, that will acceleration will be equal to minus 9.8 meter per second. This is for upward direction. So here we know that to calculate since we don't know time, we'll make use of the third equation, that is v square minus u square is equal to 2gs. So we know that v is equal to 0 minus u square is equal to 2 into minus 9.8 minus, because the ball is moving upward. The object is moving upward and upward acceleration is minus 9.8. Downward plus 9.8, upward minus 9.8. And s is 10 meters. So minus u square is equal to 98 into 2, which is 196. 196 minus 196 minus cancels each other. We have u square is equal to root of 196, which is equal to u is equal to root of 196. This implies u is equal to 14 meter per second. So the height with which the object was thrown, the velocity with which the object was thrown upwards is 14 meter per second. So now to calculate the time, let us make use of the formula v is equal to u plus gt. Okay, time taken by the object to reach the highest point. Since we are talking about reaching the highest point, we will not use v is equal to u plus gt because it is traveling upward. So we will use v is equal to u plus at. So v is 0, u is, we calculated v to be 14 plus a is minus 9.8 into t. So 0 is equal to 14 minus 9.8 t. So minus 14 is equal to minus 9.8 t. Minus cancels each other. 14 by 9.8 is equal to t. So value of time is 1.43 second. On simplification, you will get the time taken to be equal to 1.43 second. So to reach the maximum height, the time taken by the object thrown upwards is 1.53 second. So in the next class, we'll learn about thrust and pressure, and also learn about buoyancy, the property of buoyancy in objects, and then we'll finish the lesson off with Archimedes principle. So this is all for today. Thank you.